Hello friends, welcome back in this video lecture. Here friends, we are going to see bioinorganic chemistry topics, and our today's subtopic from this bioinorganic chemistry is thermodynamic aspects. Okay, under the concepts of inorganic chemistry which are applicable in bioinorganic chemistry. Means here in this lesson or in this topic we will see what are some basic concepts, what are some basic ideas of inorganic chemistry that are applied, that are utilized by the biology, by the inorganic chemistry, and hence in bioinorganic chemistry. So we will discuss all these concepts one by one. The first concept is thermodynamic aspects. Okay, so in thermodynamic aspects we are not going to see the thermodynamics behind this, but the very well known concept of acids and bases, which is related to, or which is the expansion of Levy's acid base theory. Okay, and that concept is nothing but HSAB concept, or hard soft acid base concept. In short, it is called as HSAB concept. HS hard and soft, AB are acids and bases. Actually, this HSAB concept is the elaboration of Levy's concepts of acids and bases. We know that there are different theories have been put forth by the different group of scientists to define the acids and bases in different conditions. Okay, just like Arrhenius theory, then Bronsted and Lowry theory, then solvent solute theory, then Levy's acid and base theory, and very well known and universally accepted theory, it is Levy's acid base theory. And this Levy's acid base theory, it is elaborated by the HSAB theory or HSAB concept. Okay, so what is this HSAB concept? Actually, the Levy's acids are further classified into hard acids and hard acids and soft acids. So basically, what is Levy's acids? So Levy's acids are nothing but the electron deficient species which are able to accept lone pair of electrons, which are able to accept pair of electrons. Such chemical species we call them as a Levy's acids. And again, depending on the binding ability, depending on the binding property of that Levy's acid, these Levy's acids are further classified into hard acids and soft acids. In the similar way, the Levy's bases, we know that the definition, these are the electron rich species and they are able to donate these electron pairs to the acceptor atoms. And hence, these electron rich species, that is Levy's bases, in some cases in coordination chemistry we call it as a ligands, because ligands are acting as a Levy's bases. Okay, and these Levy's bases are further classified into hard Levy's bases and soft Levy's bases on the basis of their binding ability. Okay, and further we have to learn, we have to see some basic ideas about, or some basic concepts about this HSAB. Okay, actually this HSAB concept is very useful in determining the binding property or binding ability of any metal cation which is acting as Levy's acid with any ligand which is acting as a Levy's base. Okay, so in coordination chemistry, Levy's acids are nothing but central metal cations that are form bonds, coordinate bonds with the ligands, and these ligands are nothing but they are acting as a Levy's bases. Okay, so what are these Levy's acids and Levy's bases? First of all, we will see. So hard Levy's acids are those Levy's acids which are smaller in size. Okay, they are smaller in size than they are hard. Why they are called as hard? Because they are hard to polarize. So the polarizability of such chemical species, such acids, is very less. They are very hardly polarized. Okay, then they are highly electropositive. The acceptor atoms in these Lewis acids are very highly electropositive. Mind well. Okay, they are highly electropositive. So these 3 points of differences make you clear that these are known as hard acids. So we know that in periodic table, hydrogen atom is the having lightest element. Hydrogen is the lightest element. It is having only one electron, and when that electron is get removed, the resulting species is called as H plus ion or proton, and hence the size of H plus ion is very less in all the different cations. Okay, so that's why as it is smaller in size, it is acting as a hard acid. It is acting as a hard acid. Okay, so the size is very small. It is hard to polarize more. Okay, and it is highly electropositive. Okay, so these are some examples depicted in this hard acids. These are H plus, Na plus ions, K plus, Mg2 plus, Mn2 plus, Al3 plus, calcium 2 plus, cobalt 3 plus, iron 3 plus. Okay, these are the examples of hard acids. Then the next, on the contrary of these hard acids, the opposite side of acids, they are called as soft acids. So what are soft acids? The opposite of these. They are larger in size, they are easy to polarize, so they can be easily polarized. Okay, and they are less electropositive. Okay, so here the examples are copper 1 plus. Copper 1 plus is the cation, copper cation, okay, which is having larger size than copper 2 plus. Okay, so that's why copper 2 plus is a hard acid, while as copper 1 plus is a soft acid. Okay, and this copper 1 plus is easy to polarize, so we can polarize this copper 1 plus into copper 2 plus easily, so that's why it is soft acid. Okay, so these are the some criteria: copper 1 plus, Au, that is gold 1 plus, cadmium 2 plus, then lead, mercury, platinum 2 plus, etc. These are the examples of soft acids. Then these are acids. The second chemical species are known as bases. And what are bases? In coordination chemistry or in inorganic chemistry, let us say, the bases are nothing but the ligands that are able to donate pair of electrons to the acceptor atoms, that are metal cations. Okay, and what are the ligands in different biological processes or different biological molecules? These are nothing but the protein side chains which are having amino acids residues. Okay, all amino acids are made up of different combinations of carbon, hydrogen, oxygen, sulfur, phosphorus, etc. Okay, nitrogen is there. Okay, so these protein residues or amino acid residues in these they are acting as donors or ligands. Okay, then nucleic acid residues such as DNA, RNA, okay, their side chains. Okay, and organic cofactors, these are the examples of donor atoms sources in biological molecules or biomolecules. Okay, and they are acting as a ligands. So these ligands or bases again classified into hard bases and soft bases. So what are the criteria to call them as a hard bases? These are the donor atoms in these ligands are smaller in size. Okay, as the word is hard, they are smaller in size. Okay, they are harder to polarize and they are having high electronegativity. This point of difference must be remembered. Okay, so they are hard acids are high electropositive and hard bases are high electronegative. Okay, and the examples are H2O. See, we know that the donor atom in this water molecule is oxygen atom, and this oxygen atom is highly electronegative in nature. So that's why the molecules or anions in which oxygen atom or nitrogen atom, they are acting as a donor atom in these ligands or in these bases, they are called as hard bases. Okay, so water OH minus, then carboxylate anions CH3CO minus, then carbonate anions CO3 minus, then nitrate anions NO3 minus. Okay, then ammonia and primary amines. Here the donor sites are nitrogen atoms. Here in all these examples the donor sites are oxygen atoms, which are highly electronegative and they are hard to polarize. Okay, so the last subtopic of this HSAB is soft bases or soft ligands. Exactly opposite to this. So donor atoms, they are larger in size. Okay, here it is smaller, here it is larger in size. Then they are easy to polarize, and the donor atoms are less electronegative. They are less electronegative. Okay, so the examples are the ligands or bases containing sulfur and phosphorus atoms. Sulfur and phosphorus atoms. Okay, such molecules are ligands. They are acting as a soft bases. Okay, for example, sulfides, then sulfide anions, then thiols RSH, then hydride H minus, then phosphines or alkyl phosphines, etc., in which donor sites are sulfur and phosphorus. Okay, so this is the concept of HSAB. Now the application of this HSAB concept in the bio-inorganic chemistry, that we have to learn here. So what is the actual concept is, the HSAB concept is based on HSAB principle. And what is this HSAB principle? A very famous HSAB principle is that hard acid prefers to combine with hard base. Hard acid prefers to combine with hard base, and soft acids prefers to combine with soft base. This principle is known as hard soft acid base principle or HSAB principle. Hard acid it mostly combines with hard base, and soft acid mostly combines with soft bases. There are some borderline acids and borderline bases are also present in between extreme hard and extreme soft acids, as well as in extreme hard bases and extreme soft bases. There are some borderline acids and bases are also present, and the properties of these are in between the extreme two species. Okay, so this is the HSAB principle. Now according to this principle, our molecules or biomolecules or the biological reactions, biochemical reactions that are occurring in life processes or in our body, that are also fulfilling the criteria, they are also following the thermodynamic aspects of HSAB concepts. For example, when a crystal of protein, when a crystal of any protein that is in solid state, when we soak that protein in a solution of potassium tetrachloroplatinate, potassium tetrachloroplatinate, in which this potassium, when this molecule is dissociated, it is forming 2K plus ions and PtCl4 2 minus ions. Okay, so here the platinum is in plus 2 oxidation state, platinum is in plus 2 oxidation state. Okay, now the platinum plus 2 oxidation state, that's this one, Pt in plus 2 oxidation state, is soft acid. Okay, now we have a metal cation, that is platinum plus 2. This is platinum plus 2 is a soft acid. Now when we add a protein crystal into this solution dissociates into these ions. Okay, here the platinum has some options to get combined with. So we have added protein here, so the protein may have different side chain amino acids. Okay, or there may be different amino acid residues possible, or they are available for the binding with the this platinum 2 plus metal cation. Okay, now as this platinum 2 plus is soft acid, it according to our HSAB principle, this soft acid prefers to combine with soft base. Okay, so it mostly prefers to combine with that amino acid residue which is having a donor atom of the soft base type, because soft acid is platinum 2 plus, it prefers to combine with soft base, and hence the protein may have oxygen donor atom ligands, sulfur donor atom ligands, phosphorus donor atom ligands, nitrogen donor atom ligands, okay, in the nucleic acid side chain or protein side chain, but this platinum 2 plus prefers to combine with the cysteine, or methionine amino acid residues. Why? Because both of these cysteine and methionine amino acid residues, they are having sulfur donor sites, and this is what we called HSAB principle. Our body, our biology or biochemical reactions, they are also fulfilling the criteria of HSAB principle. Hence, as there are a number of possibilities are there for the binding of this platinum 2 plus with different ligand sites in the amino acid residues or nucleic acid residues, but it is preferentially bonding with the cysteine or methionine, in which the donor sites are sulfur atoms. Why? Because sulfur donor site is a soft base and it does not binds with the donor atoms, in which it does not bind with the amino acids in which donor sites are oxygen atoms or nitrogen atoms. For example, aspartate. So aspartate or glutamate, they are having oxygen as a donor sites in their side chains in that amino acids, but platinum 2 plus is trying to, or it is preferentially binds to methionine or cysteine, in which donor site is sulfur. This is the case of, or this is the illustration of HSAB concept or HSAB principle. Okay, and that is fulfilling by our biochemical reactions. Okay, now the next concept is the Chelate effect and Irving William series. Okay, so we know that what is meant by metal ion, then ligands, what is meant by chelate, what is meant by chelation. Okay, so let us revise these concepts. So what is metal cation? When metal cation is forming bonds with the one ligand, and that ligand is having more than one sites of donation. Okay, for example, a polydentate ligand means that ligand is only one ligand, but it has number of donation sites. The donor sites of that ligand have more than one. Okay, when such polydentate ligand is forming a bond or forming a coordinate complex with the central metal cation, that process is called a chelation process, and the resulting coordinate complex is called as chelate complex. Okay, and this chelate are having extra thermodynamic stability due to the chelating effect. Okay, that can be explained by the example of when hexaco-nickel 2 plus, this coordinate cation, this complex cation, when it is treated with H2 EDTA 2 minus, okay, so this EDTA is a polydentate ligand, more specifically it is hexadentate ligand. Okay, it is having 6 donor sites. I am trying to draw the structure of this EDTA. So what is EDTA? So it is ethylene diamine. So CH2 ethylene diamine, okay, ethylene diamine, and it is having tetraacetic acid. So CH2, 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 COOH, CH2, COOH, CH2, COOH, and here CH2, COOH. So this is a neutral salt, neutral molecule called as ethylene diamine tetraacetic acid. Okay, it has 6 donor sites, 1, 2, 3, 4, 5 and 6. Okay, so this is a hexadentate ligand. Okay, and in this complex the water is acting as a monodentate ligand, and there are 6 monodentate water ligands are present. They are coordinated to the central nickel 2+ cation. When we treat this complex with EDTA ligand, then these water ligands are get substituted, they are get replaced by this hexadentate EDTA ligand. Why it is so? What is the reason? The reason is that the Chelate effect. Now how we can explain that all these water molecules ligands are substituted by this one EDTA ligand? Because this EDTA is a polydentate hexadentate ligand, and one EDTA molecule can combine with one nickel 2+ cation. Instead of one nickel metal cation here, it is combining with 6 water molecules. Okay, so this is the effect known as Chelate effect, and this chelate, once it is get formed, it is having extra stability. Okay, and due to this extra stability, the chelate complexes are very, very stable in nature, and hence these EDTA, due to the extra stability, generally added in the body system when someone is get poison or some toxic effects have been found. Okay, then to remove that particular metal cations, that EDTA is get added. Okay, for example, mercury 2+ is mercury poisoning takes place, then lead poisoning takes place. In such cases, this EDTA ligand is get added, and that mercury cation and lead cations are get extracted with the help of this EDTA ligand, because once they are getting formed in our body fluids, they are not broken by water molecules which is present in our body system, and hence they can be removed or they can be extracted, and hence detoxification process can be done very easily. So this is the analogy of bioinorganic chemistry with that of the some biological process that can be occur, that can be possible in the our biological systems. Okay, then one of the important application of this Chelate effect is in the Irving William series. So what is this Irving William series? We know that porphyrin and chlorine rings, in these rings, these are macrocyclic molecules in which 4 pyrrole molecules, 4 pyrrole rings, which are mostly planar in nature, they are arranged in cyclic manner. Okay, in such a way that the nitrogen donor atom is pointing towards the central cavity of that ring or of that cycles. Okay, in first lecture of this bioinorganic chemistry, we have already seen the structure of this porphyrin or chlorine ring. Okay, so a cyclic structure is there in which 4 pyrrole rings, 1, 2, 3, 4, in such a way that, okay, 4 pyrrole rings are arranged in a cyclic manner, and they are arranged in such a way that the donor nitrogen atoms are pointing towards the central cavity of that ring, and in that central cavity different metal cations can accommodate. Due to this inner cavity of that rings, different metal cations are able to accommodate in that cavity. Okay, and due to this, different combinations of these metallomorphins and metallochlorines are possible. Okay, for example, here in cytochromes the central metal ion present in this metalloporphyrin or metallocorine is iron. Okay, remember these metal atoms, they can be asked in your examination. In cytochromes, the iron is present in central portion. In vitamin B12, that is in cyanocobalamin, the central metal ion is cobalt. In chlorophyll, the central metal ion is magnesium in the corine or porphyrin ring. Okay, now what about this Irving William series? This series is explained by the Irving and William first time, and they are explaining about the in some metal cations, as we move from left hand side to the right hand side of the periodic table in a given period, the atomic and ionic radii are getting decreased. Atomic and ionic radii are getting decreased from left to right in a given period. Okay, so due to this, as size is going to decrease, and we know that small size cations are known as hard acids. Okay, and as the size of that metal cations is get reduced or it is get decreased, the bonding between that metal cation and that ligand is getting stronger and stronger, and this effect or this series is known as Irving William series. Okay, and the series is like that. The size of calcium 2 plus ion is less than magnesium 2 plus, less than manganese 2 plus, less than iron 2 plus, less than cobalt 2 plus, less than nickel 2 plus, less than copper 2 plus, which is greater than zinc 2 plus. Why the size of zinc 2 plus is greater? Because it is completely filled, d subshell is completely filled. Okay, only 4s electrons are lost and there is a formation of Zn2 plus ions. Okay, and hence the size of Zn2 plus ion is less as compared to the copper 2 plus ions. Okay, so that's why this series is known as Irving William series. And what is the analogy of this Irving William series? Smaller the size of metal cation, as we move from calcium 2 plus to copper 2 plus, the stronger is the bond between that central metal cation and the ligand. Okay, so metal ligand ball is getting stronger. Okay, so this is all about the Chelate effect and Irving William series. So in this today's lecture, we have learned about some thermodynamic aspects which is totally related to the HSAB concept, HSAB principle, and the Chelate effect of the bioinorganic chemistry. Thanks for watching. Have a nice day.